Hello everyone and welcome to this quick video on the refractive index. Now I'm hoping that before you watch this video you already have an understanding of what we mean by a refractive index. However, there's going to be a bit of review of that in this video. We're also going to learn a new equation to calculate the refractive index and just have a chance to discuss the ideas which we're seeing on the screen in a bit more detail. So let's start with the idea of refraction. Refraction is simply when we have a ray of light, in this case, which bends, which changes its direction as it travels from one medium to the other. Now in this case, in the picture you can see on the screen, we're traveling from air into another medium, and that's going to be important. So this angle I that you can see on the screen, that is going to be measured in the air, and the angle R is measured in another, what we might call optically dense medium. And what we're going to do is we're going to calculate the refractive index of that medium. Put simply, when we want to calculate the refractive index, there's one way of calculating it, which is simply to find the ratio of the sine of each of these angles. You can see here we've got sine of angle I and sine of angle R. Now, it's important that you make sure you're working in the correct units in this case. Usually this will be expressed in degrees, so you need to make sure your calculator is ready to measure in degrees. When you use the sine function, if it's got a different setting, it will give different numbers. So please check that you've got degrees set on your calculator. This is n is equal to sine I over sine R. Okay, here in this case, we call I the angle of incidence. And again, that's measured in air for using this equation. R is what we call the angle of refraction, and that is inside the medium. So in this case, inside the grey box. N is just this quantity, the refractive index. Now, the refractive index is a number which is associated with a certain material. So glass has its own refractive index. Water will have its own refractive index. Perspex will also have its own refractive index, and so on. It's a number with no units, so we simply say that the refractive index is 1.2, 1.3. We don't need to express it with any units, and that's one of those rare occasions that we have that in physics. Now, you may be wondering at this stage what the refractive index means. Well, this is something that we have dealt with in the beginning of my lesson anyway, but I just thought I'd recap it here. The refractive index gives us an idea of the speed of light. We know that in air, the light travels with a speed of 3 times 10 to the 8 meters per second. That's 300 million meters per second. Well, when it goes into a material, it slows down, and it's going to slow down by a factor of n. So if n is 2, then that means the speed of light will reduce by a factor of 2. If n is 1.45, then it will reduce by a factor of 1.45. So this n is really important because it expresses how much slower light will go when it is moving in the new medium. So it may be a good opportunity at this stage to pause the video and write down these two equations which look at n. One of them is the sine of the two angles, the ratio, and the other one is just simply the one which expresses the light slowing down. I suggest you pause the video now, and if you're ready to go on, we'll try an example. So let's go for it. We'll use the same diagram here, but we'll just put some values in for angles. Now I'm just using simple angles here. Let's imagine we measured 45 degrees and 30. Okay, now what we want to do is we want to we want to calculate the refractive index, but we'll just check here. Does this make sense? We're going from air into a more dense medium, a higher N medium, and so if we're expecting the light ray to slow down, and that makes sense, that means we're going to bend towards that dashed line, the normal line here. So this looks good so far. When we're using this equation, we're always expecting bending towards, we're always expecting I to be greater than R. We're just going to calculate it. Well, n is equal to sine I over sine R, and again, you might want at this stage to pause the video, put in the values in your calculator, and just check that you get the same as me. I'll assume that you've done so, and let's carry on. So we've got sine I over sine R, sine of 45 degrees over sine of 30 degrees. Now when I put that into my calculator, I get 0.707 on the top and 0.5 is equal to 1.414. Now this is a really sort of typical number of the refractive index. The numbers are always greater than 1 because we're expecting the light to slow down. And it's usually between the range of 1 to 2. Okay, if you're getting huge numbers, 15, 16, 17, then there's probably something going wrong here. Okay, if you're getting the order of 1 to 2, then that sounds about right for an everyday sort of normal material. And again, notice there are no units because this is a dimensionless number. Now, this is our refractive index. What we could do is calculate the speed of light in this medium. But what we would do is take 3 times 10 to the 8th, that's that speed of light, in a vacuum anyway, and divide it by 1.414. Okay, and we're expecting a number which is slower. Okay, well, there you go. 3 times 10 to the 8 divided by our n, 1.414, gives me 2.12. Okay, again, a little bit of a sanity check. If you're getting a number which is greater than the speed of light here, then that suggests that something's gone wrong because the speed of light is our kind of speed limit, okay? We tend to not deal with numbers greater than the speed of light when we're expressing speeds. Okay, as usual, I hope that makes some sense. And if you've got any questions, please let me know. If you're ready to go, let's get cracking with the next part of the tasks. Thank you for watching.